In this video lesson, we will continue to work through the exploration sheet that covers short-run behavior of rational functions. We'll be starting with number 3 on that sheet, which is on page 3. Number 3 is basically asking you to sketch the graph of a given rational function when you know what the formula is. And to be able to do that, of course, this would be without a calculator, is we need to kind of determine several things before we actually sketch the graph. Okay, the first, as it says, is any discontinuity, and by a discontinuity we're talking about either a vertical asymptote or a removable discontinuity. And we know that both of those are going to happen when the denominator equals 0, right? So we're looking for when q of x is equal to 0. Now, of course, with the removable discontinuity, we would also be looking for p of x equals 0 as well, right, where we would have identical factors on the top and bottom. After the discontinuities, we'll be looking at determining the long-run behavior of this rational function, and that would include determining if we have any horizontal asymptotes or not. And of course there we're going to be looking to put the leading term of the top polynomial over the leading term of the denominator polynomial. And that should simplify to give us some power function that we can then analyze. The last two things we'll find before we graph should be familiar to you. We'll be looking to find any x-intercepts that we might have, as well as what the y-intercept would be. Of course, to get any x-intercepts, we just set y equal to 0 and solve for x. And to get the y-intercept, we set x equal to 0 and determine y. Once we have all this information, we'll be ready to sketch the graph. Let's start off by doing Roman numeral 2 together. It's a little more basic one than Roman numeral 1 is, so I thought we could start with this one. So we're going to first look for a discontinuity that we might have, either vertical asymptote or removable. And of course, we know this function is going to be not continuous. It's kind of very similar kind of problem to, what's the domain of a function? We're looking for where there's a break in the x values. And of course, that would be happening when our denominator is 0. So we just set our denominator equal to 0 and solve, and we get that x will equal 2. And we know that that's going to be a vertical asymptote because we're not able to cancel this factor, right? Remove the discontinuity with an identical factor up top. Also, another way we can know it's a vertical asymptote is when we do plug 2 into the function, we get 8 over 0. If it was going to be removable, we would be getting 0 over 0. So I'm going to go ahead and draw in this dashed line for my vertical asymptote. All right, moving on to the long-run behavior. We can take a look, right? We want to get the highest degree term from both the numerator and denominator. So we will just have, 3x over x, and that simplifies to just 3. So this is, of course, as x approaches plus or minus infinity, looks like we're going to have a horizontal asymptote of y equals 3. So now I've drawn that feature in, and now we can just take a look at the intercepts. Let's do the x-intercept first by setting our output value equal to 0. Now you might think this is a fairly daunting task to solve this equation, but the first thing you're going to do is to kind of get this denominator out of here by multiplying both sides by x minus 2. And of course x minus 2 will cancel on the right side, but on the left side is just times 0. So we're just going to end up with the numerator equal to 0. Another way to think about doing it is just to set the 0 over 1 or over any number and cross multiply. And of course that'll leave you with just the 3x plus 2 times a 1 and then equal to x minus 2 times 0. So you're just going to end up with the numerator, as I said, equal to 0. And that's going to happen every time, right? So essentially, to get an x-intercept of a rational function, you just set the numerator equal to 0. Okay, so there we have it notated, numerator equal to 0. And if we continue solving here, we will get that our x-intercept is at negative 2/3. Okay, only one x-intercept here for this graph. And I've marked it here at negative 0.66 repeated. All right. And the last piece of the puzzle we need is just the y-intercept. That's usually a little easier to get than the x-intercept because all we got to do is plug 0 in for x. All right, so I think we're ready to sketch our graph. We have some markers, so we have to go through our x-intercept, we have to go through our y-intercept, we have to conform to this vertical asymptote, our curve does, and our curve has to conform to the horizontal asymptote. So I think it's pretty clear it's just going to come down like this. That may be about as good a job as I can do with the curve. All right, now what's not quite as knowable is what's going on the other side of the vertical asymptote. All right, you always have to check on both sides. There is something going on here. Now it's possible that the curve could conform this way down on the bottom, but it's probably not very likely since, remember, we only found one x-intercept. So my guess is that the curve is going to be conforming up here above the horizontal asymptote. But let's plug in a number just to check and make sure. So let's plug in 3 to see what happens. All right, so indeed it does look like we're going to be up top because when we plug in 3, we're getting back 11 over 1. So we'll draw on our curve up above. All right, so there we go. We have found all the main features of our graph, and we were able to sketch a pretty good graph of this.